Hello and welcome to our lesson on waves, I thought it was going to be really smooth then. Part 3. Oh no, it's really skinny. Part 3. So you've already seen two videos. One on general waves, progressive waves. One on constructive, destructive, superposition, etc. And today we are going to look at stationary waves. So I'm going to scroll on down here. So much. Thank goodness it wasn't all in one. Now it's actually only a very short video, which makes life nice and easy, and then we will just go on and start practicing. So, stationary waves, and again, this is a memorization one, I'm afraid. When two identical waves travelling in opposite directions cross each other, they interfere with each other to produce a wave shape that stands still. The product is called a stationary wave. Stationary wave can either result from interference between two identical waves travelling in opposite directions, going to be an S there, or a wave interfering with its reflection. They also have things called nodes and antinodes. Nodes are places where or points on the wave where displacement is always zero. Antinodes are points of greatest amplitude and intensity. There is no transfer of energy in a stationary wave. So if a question asks you how a stationary wave is formed, I want you to combine these two slides, because you say here how it's created with the superposition. In fact, let's get that word in. Superposition of two waves travelling in opposite directions, possibly with a reflection of the other end. And then you talk about the fact that there's nodes and antinodes and there's no transfer of energy. That is how you gain those marks on those questions. Now, I know you can't really see it, so I apologise for that. In fact, let's have a little look, shall we? Stationary wave. Yes, I just really want to... here we go.
The node is...
Oh, stop talking.
Constructively interferes with the next wave that comes down right at this point.
Where's the
now
volume?
The waves that reflect...
I don't want him. Right, I actually just want to show you this picture, really. So, here we've got a stationary wave, and if you remember we did this demo in class. You've got a piece of string, you've got a motor oscillator on one end, and then it vibrates off. Can you see that pole on the right-hand side? So, key things to note are, you can see there are three nodes on this stationary wave. Between two nodes, so let's look at the two nodes on the right-hand side and that antinode in the middle. Everything between those two nodes will be moving up or moving down at exactly the same time. They all move up, they all move down, they all move up, they all move down. Now that means that everything between those two nodes is in phase with each other. On the left-hand side, that is also true. They all move up, they all move down. However, their motion will be the opposite direction to the node next to it. So when everything on the antinode on the left moves up, everything on the node section on the right will move down. So although between two nodes everything is in phase, in comparison to between the next set of nodes next to it, they are in antiphase. So that's not actually what I want to show you, but hey ho, right. So that leads, that leads on to here. Yes, here we go, right. For this standing wave on a string, each point has a different amplitude to its neighbour. All the points between two adjacent nodes are in phase with each other because they all move up. The points on the left are pi rad out of phase with the points on the right side. So hopefully you can see that from that diagram. On the left, they're all moving up. On the right, they're all moving down. So, yeah. No, don't want that. Okay. Plucking a string will cause a progressive wave to travel along the string and reflect off the end, causing a stationary wave. Lovely. The standing wave will have a fundamental frequency, F0. F0 is the lowest frequency that you can cause a stationary wave on. This depends on the string's mass, tension, and length. The wavelength of this wave is 2L, length of the string. And now, apologies, I have a better PowerPoint for this, but because I can't get into my document still, I'm going to have to just draw it. Now, there are three different ways of constructing stationary waves. You have on a string, and on a string, the two ends of the wave are nodes. They are held in place. And so you end up with patterns that look like this. etc. So the key bit here is each end is a node. Now in terms of frequency, this one is f0. This one is 2f0. And you can see if you double the frequency, you'll end up with that nice stationary wave pattern. And this one is 3f0. Lovely. Now let's look at the wavelength, and more importantly, the wavelength in comparison to the length of the string. So just to clarify, wavelength. Between the 2 points on the string, you have half a wavelength in that fundamental frequency. Can you go up and then to the middle? And obviously to make a full wavelength, you'll then want it to go down and to the middle. So it will be 2 lengths of the string there. In the next one, you can see hopefully that you've got 2 of those sections. Each one is a half wavelength, so you've got a whole wavelength there. The next one, you can see you've got 3 sections, so 3 half wavelengths. So to find the wavelength, you do 2L over 3. Okay. The way I tend to remember it is that basically you do 2L divided by however many sections you have. So the top one, you've got 2L divided by 1, gives you 2L. The next one, you've got 2L divided by 2, because there's 2 sections, gives you L, etc. 2L divided by 3, and so on and so forth. That's the kind of pattern that I work out to do that. So that's a string. Each end is a node, and that's the frequency. Then let's look at a tube closed at one end. Okay, and I'll go sideways just to keep us consistent. And again, I'll do 3. Now, at the end that it is closed, you will always end up with a node. At the end that it is open, you will always end up with an antinode. So our lowest one that you can have, our fundamental frequency, is that. Node at one end, antinode at the other. The next one, the only way it fits in is like that. The next one, there we go. So again, this is just me knowing that there's got to be an antinode at that open end. So let's look at frequency. If this is frequency 0, can you see, and we'll look at wavelength here, can you see that that is quarter of a wavelength? That's not a whole half wavelength even. It hasn't even got back down to 0. That's a quarter of a wavelength. So this will actually be 4L. Actually, I don't like it. No, you know what? Sorry, ignore that bit. Right, yeah, so that's frequency 0. This is a quarter of a wavelength. That's a better way of doing it. Then, if we go to the next one, can you see you've now got 3 times as much of a wave put in there? Like here, and that first section is equivalent to the whole thing there. So this is actually 3 times the fundamental frequency in order to get that. And you've got 3/4 of a wavelength. In the next one, it's actually 5 times the fundamental frequency, and you've got 5/4 of a wavelength. And basically, notice the fact that here they go up in odd numbers. So, and again, you can figure all of this out. I just figured all of that out by looking at it, by knowing the fact that it had been node and antinode. But if you don't remember the node and the antinode, that's where it will really trip you up. Okay, and then our final one is a tube open at both ends. And here, just like in the tube that was closed at one end, everywhere, there's an open end, you need an antinode. So you're going to have an antinode at both sides here. So the first one is like that, with a node in the middle there. Then the next one, I've got to think about this carefully. So you've got 2 nodes there. And next one, lovely, 3 nodes. Okay, they're very dodgily drawn, but you're hoping to be seeing that. Let's look at frequency. If this is a fundamental frequency, this is twice the fundamental frequency, and this time is 3 times the fundamental frequency. Nice and easy. So look, you'll notice it's very, very similar to that, but as opposed to having nodes at either end, it's an antinode at either end, basically. And again, now let's look at wavelengths. You've got half a wavelength. Each one of these is a quarter. You've got 2 quarters there, so that is half a wavelength. Then here you've got a whole wavelength. I know it looks a bit weird, but you go from, if you think peak here, down to the trough, and then up to peak again, that's a whole wave. Here, you've got 3 wavelengths over 2. So again, check out the fact, you know, I did this in a really weird way. Let's get rid of this and do back to, there you go, apologies. Let's do it in the same way. So this was half a wavelength, that was a whole wavelength, and that was 3 wavelengths over 2. That's a much better way of doing it. Why did I not do that? Apologies. So yeah, it is the same. Look, tube with both open at both ends, it is the same as in a string that is closed at both ends, except that each end here is an antinode. Right, I think that was everything for stationary waves, so I'm hoping that was fairly short and not too confusing, and now we'll go do some questions on it. So I shall see you later. Bye!